So let's consider, what if we have charge in a ring? Okay, so we can imagine just a ring of charge right there. So a circle of charge. So a circle of charge. So this is like a wire that is bent into a complete circle. So we're going to say this is radius r to the center of it. And so I want to know what is the electric field there. Now, if you look at the center of that circle, then what happens is, notice something interesting. At the center of the circle, we got charge right here, and that makes an electric field. But if this is a uniform sort of thing, there's also, wherever you are on the circle, there's some dq, but there's another dq on the other side that's exactly balancing. So what does that do? It means at the center, the electric field is zero. What if we're not in the center? Okay, so what if we're not in the center? What if we're some distance d off center? Okay. Then the electric field here is going to be stronger than electric field over there. So you might look at it and say, well, now this is going to be a lot more complicated. And so we want to know, what is that? Okay. Well, it turns out it is, in fact, a lot more complicated because now the electric fields are now going at different angles here in all sort of ways. And so this is so complicated, we're not going to do that in this class. That's beyond the level of this class to do something that is that complicated. And so we're not going to worry about that. And that's for an upper division class. For those that might go into electrical engineering or physics, you'll have to worry about that sort of thing. In fact, that is so complicated, it's probably not going to be something you would see unless you were in graduate school, because the mathematics is non-trivial in that case. Okay, what we're doing in this semester is we're taking simplifying conditions, simplifying assumptions, just to make the math a little bit easier for us so that we're not going to overwhelm ourselves. And so we're not going to do that. But what we could do is, say for our ring of charge, we might say that it's not a complete ring. It's just an arc of charge. And so I want to know, for an arc of charge, what is the electric field. So what we're going to do is we're going to assume that arc is a fraction of a circle. Okay, so it's a fraction of a circle right here. So here's our arc of charge right there. So we put some kind of charge on there, and it spreads out along that arc. Okay, and so what I want to know is, in that case, what is the electric field at what would have been the center? Now, why do I make it at what would have been the center? Because now, for some little dq, the electric field's this way, and it's balanced by a dq that way, so that the y components cancel and the x components add. Some little dq there is like this, dq there is like that, and again, for both of those, the y components balance and only the x components remain. Okay. And so that means that makes this a little bit easier, because we only have to do the x components. Okay, and so what I need to know, therefore, is for our ring of charge, if I bisect it, if I say this entire ring of charge is some angle theta, then if I bisect it, then it's going to plus, so we're going from the center, we're going to plus or minus phi, where phi is 1/2 of theta. So from minus phi to phi is going to be from minus phi to phi gives us 2 phi, and so that's going to be theta. Okay, so So we only want it's part of a big circle here, we only want the DEX. Okay, so that means if we got some DQ right here, and that DQ is some angle psi up like that, that's going to be some angle psi there. So that DQ makes a DE like that, so the DEX is going to be equal to the DE times cosine of psi. Okay, so DE is going to be K dq over r squared. Okay, now what's dq? So if the charge is spread out, we'd said before that dq equals lambda dx, that's even a straight line. Well, this isn't a curved line. So for a curved line, we have an arc of length s. So the dx should really be ds. Okay, so what is ds? That's this length here. So what is s? S is the length of the arc. So if the entire thing is some angle theta right there, then S is going to be equal to R theta. Okay. And so that means that ds would be lambda r d theta. Well, in this case, we're not calling it theta necessarily, we're calling it psi. So it'd be r d psi. Okay. So dE is going to be equal to K sub B. The dQ is lambda r d psi and divided by r squared. So those r's cancel. So that's going to be K sub B lambda d psi divided by r. Now, so psi is like that. We're going from minus phi to phi. So E is going to be the integral of the dE cosine phi. So that's going to be the integral of K sub B lambda cosine psi rather d psi divided by r, going from minus phi to phi. Okay, so you look at that and say, well, the electrostatic constant Ke is a constant. Lambda is going to be a constant, so that comes out. R is the center of the arc of this curvature, so that's constant. So this becomes K sub B lambda over R, integral from minus phi to phi of cosine psi d psi. Okay. Well, integral of the cosine is the sine. So that's going to be sine of psi evaluated at minus phi and phi. Okay, so that's going to be equal to K sub B lambda over R, and that's going to be equal to sine phi minus sine negative phi. So that's going to be equal to K sub B lambda over R times 2 sine phi. Okay. Well, K sub B is 1 over 4 pi epsilon naught. So the 2 can divide in there, so we end up with lambda over 2 pi epsilon naught r sine phi. That's the electric field, and it's directed in a direction that is away from the arc. Okay. Now, if lambda is negative, negative away is towards. Okay, and so that's how you would do this for an arc of charge. So you may leave it, in this form up here, or you can write it in this form, which is really how the book does it. Okay, so either way is valid. So this is how you find the electric field of an arc of charge. And again, at that point, at the center of the curvature, is pointing directly away from the arc, or directly towards the arc if lambda happens to be negative. Now, remember, what is lambda? Lambda is going to be the charge divided by the arc length. So if this thing here is some radius r, and if that's some theta, then lambda would be equal to the total charge divided by the length. The length is going to be r times theta. Okay, and so that you could put that back into that equation we just came up with. Okay, because the equation we just came up with was that the electric field was equal to lambda over 2 pi epsilon naught r times sine of phi. Okay, phi is half of theta right there. Okay, so you could actually put this back in there and say, this is equal to r times 2 phi right there. And if I plug that in, this is going to be back to, well, interestingly enough, q over 4 pi epsilon naught r squared sine phi. Okay, or in other words, k sub e q over r squared sine phi. Okay, so if you happen to know what q is, then you can plug that back in and find the electric field. If you don't know q, but instead you know how it's distributed, the charge per length, then you would use that form right there of the equation. So either way, there's two different ways of expressing this.